In the last video, we talked about exponential functions and how to graph them, how they are defined. Now we're going to go ahead and focus on some applications on why exponential functions are very useful. So if you've looked at the graphs of 2 to the x and 1/3 to the x in the last video, then you notice that that 2 to the x was increasing from left to right, while 1/3 to the x was decreasing from left to right. And that's because of the value of the base of the exponential function. Okay, so anytime that you have an exponential function, whether it's b to the x, or I also like to use a times b to the x, where a is an initial amount of something. We'll talk a little bit more about that later. Then if your value of b is greater than 1, then that's a function that shows exponential growth. Exponential growth. But if on the other side of that, if b is a number between 0 and 1, because remember, b has to be positive, but it cannot be 0 and it cannot be 1. So if b is greater than 1, then the only other case is b is between 0 and 1. And that shows exponential decay. Then that's a decrease from left to right. Okay, so greater than 1, exponential growth. Between 0 and 1, exponential decay. For example, 12 times 0.95 to the x. So my base, my value of b is 0.95. That's what's being raised to that exponent of x. And it's between 0 and 1, so that's going to show exponential decay. Or if I have this time the decimal is on the outside. It's not the base of the exponential function. 2 is. That shows exponential growth, right? You can also see this in real life situations, like for example, let's say you put 1,000 into a savings account for 4 years, and let's say that account gains interest at about 5% per year. That's exponential growth, right? But there's a way that we can actually track this a little bit more based off of whether something's growing or decaying. It could be anything from money to populations of animals or bacteria, or even something like the half-life of a radioactive material, right? So, for example, let's say, so anytime that I'm trying to calculate an amount of a group of things, animate or inanimate, over a period of time, I use a general growth and decay formula, right? So, and it's given like this: A of t equals p times 1 plus or minus r to the t. Now, what does all this mean? Well, you always start out with an initial amount, a principal. That's the amount that you start with. This right here is your rate. And it should be known that it should be in a decimal form, not a percent form. Now, this right here is used based off of whether your population or whether your amount is growing or decaying. If it's growing, then you use 1 plus r. If it's decaying, then you use 1 minus r. Okay. T is going to represent time. And then this right here, A of t, is the final amount. That's the amount that you're getting back after that time has passed, right? So let's look at an example. So let's suppose that you invest $1,000 into a savings account at the end of the 6th grade. So you have $1,000 into an account starting at the end of 6th grade. The account pays out 5% annually, like 5% interest. How much money will be in the account after graduation? Furthermore, how long will it take for the account to increase to at least $1,500? Well, for the first part of the question, we need to figure out how much time passes from 6th grade to graduation. It's about 6 years, right? So 6 years. So if I apply this to the formula, right? So A of t equals 1,000 times 1 plus, the count's growing, 0.05 to the 6. Let's go ahead and calculate that. So I got 1,000 times 1 plus 0.05 to the 6th. And we're going to round to 2 decimal places because we're talking about money. Then that's going to give us a total of $1,340.10. So that's how much money will be in the account after graduation. So you have gained $340.10 in interest on that account. Second part of the question is, how long will that take? How long will it take to get to at least $1,500? Well, I'm already at $1,340.10 after 6 years. Let's see how much 7 years would be. So for 7 years, we'll raise this to the 7th power instead of the 6th. That's 1407.10, not quite what I'm looking for. Let's go 8 years. For 8 years, it's 1477.46. Again, still not quite. Let's go one more. Let's go 9. There we go. 1551.33. So somewhere between 8 and 9 years is about how long it'll take for that account to grow to at least 1,500. Judging by this, maybe about halfway between those two, somewhere between maybe March to June, if I had to take a guess. Also, let's look at another example here. So let's say in 2003, a study began exploring the dwindling numbers of the Iberian lynx. At the beginning of the study, there existed 150 of these animals. So in 03, it's 150 of these cats. In the year that followed, in 2004, only 120 remained. About when would, if this trend continues at an exponential rate, how many of the Iberian lynx will be left in 2014? Well, first off, we need to know what percentage of the lynx of these animals died out in that 1 year, right? So from 2003 to 2004, we had a loss of 30 Iberian lynx. If I take that and divided it by 150, that's about a fifth. So that's about 20%. So that's a 0.2 decrease. If that trend continues exponentially, we can use the formula, the exponential growth and decay formula, to determine how many there'll be left in 2014. Well, let's figure that out. Now, what's our value of t going to be? Well, how many years since 2003 passed? That's about 11, right? From 2003 to 2014. So my initial amount was 150 times 1 minus 0.2 to the 11th. And let's see how many will be left. Let's see. 150 times 1 minus 0.2 to the 11th. That's about, if I round to the nearest whole number, about 13 left. About 13 of these animals left. Now, second part is, how long will it take for them to go extinct? What value of t do I need to reach to make this 0? Well, I'll let you guys figure that out on your own. In the previous example, when we talked about the savings account, we assumed that interest was accrued annually. That's not the only way interest can accrue, right? That's where we use what's called compound interest. Sometimes interest accrues over a period of time, multiple times within a year. Sometimes interest compounds twice a year, 3 times a year, 4 times a year. So there's a formula that we can use to calculate what's called compound interest. So we can find the amount of our account or of whatever. We can find that amount after those many years, after so many compound interest compounding more than 1 time a year. All right, so this is called a compound interest formula. And there's actually 2 types. So compound interest. So we have A equals P times 1 plus R over N to the N T. So the same variables apply except we're adding a new variable, N. N is going to represent how many times interest accrues over the course of 1 year. So for example, if interest occurs annually, then N is 1. And it's pretty much the basic general growth and decay formula. Now, if we're talking about semi-annually, semi meaning half, that means every half year. So that means that N is going to be 2 because interest is compounded twice a year. Quarterly, I like to think of it as, with the word quarter, like a quarter of a school year, quarter of a football game, quarter of a basketball game. N would be 4. Monthly, of course, there are 12 months in a year. Weekly, that's 52 weeks in a year. Daily, and we'll just assume that we're not in a leap year, so we'll use the number 365. There's also another type of compound interest, and that's called continuous compound interest. That means that once interest starts compounding, it never, ever, ever stops. Like, let's say I have money in an account that interest accrues continuously. That means as we're talking, that interest continually piles up. That's called a continuous compound interest. So for continuous compound interest, it's a simpler formula. A equals P times E to the RT. So it's not P times E times R times T. No, it's P times E to the power of R times T. And variables are still the same, except I'm not using N, and the base of my exponential function is E. Okay, so let's look at an example here. Suppose you win a contest at graduation that deposits $3,000 into an account that accrues 7% interest. We want to write that as a decimal, 0.07. When you graduate in college after 4 years, so already we're given a value of time, 4. How much money will be in the account if the interest accrues either annually, monthly, daily, or continuously? So I have an initial amount, I have my R, I have my T. My N, we'll have to compute the formula 4 different times. Once for annual, again for monthly, daily, and then continuous. And then for the last one, we'll use the continuous formula. All right? So A, N being 1, right? That's A of 4, because 4 is the number of years, equals 3,000 times 1 plus 0.07 over 1 to the 1 times 4. Now, some of that can be reduced, right? 3,000, 0.7 over 1 is itself, plus 1, that's 1.07. 4 times 1 is 4. So sometimes it helps just to simplify the formula before you actually put it in your calculator, so that way you're not confusing yourself. So 3,000 times 1.07 to the 4th, that is 39, 32, 39. Because remember, we round to 2 decimal places because we're talking about money. Okay. Let's go monthly. N is 12. N is 12. So that means that we'll take 3,000 times 1 plus 0.07 over 4. I'm sorry, 12. Sorry. To the 12 times 4. Sometimes it's best to just do these things one at a time, like using order of operations. Like first off, figure out what 0.07 over 12 is. 0.07 over 12, that's, I get this decimal right here. So I'm going to add that to 1. Then I'm going to raise that to the 12 times 4. Well, 12 times 4 is 48. So I'm going to raise that to the 48th power here. And then I'm going to multiply that by 3,000. And I get 396616. All right. I'm going to do the same thing again for daily. 3,000 times 1 plus 0.07 over 365 times 365 times 4. So 365 times 4, that's 1460. I'm going to have to remember that. 1460. Okay. All right, so again, I'm going to do these one step at a time. 0.07 divided by 365, and I get this decimal right here. Okay, now I'm going to add that to 1 and raise that to this exponent, 1460. Then I'm going to take that number, multiply it by 3,000, and I get 3969.28. Okay. For the last one, for the continuous case, again, all I have to do is just use the continuous formula. All right, so that's A of 4 equals P, which is 3,000, times e to the 0.07 times 4. So 0.07 times 4, that's 0.28. To the 0.28. Yeah. So I'm going to raise e to that exponent, so 3,000, e to the 0.28. So something that looks kind of like this. And that's 3969.30. The more, and what you'll notice is that the more and more that interest is compounded, the smaller and smaller the amounts get closer to each other. For example, if we're going from annually to, from annual to monthly, or annually to monthly was a big jump, but then from, daily to continuously, only like maybe an 11-cent difference, right? There's one more application for compound, or for growth and decay that I want to go over briefly, and it's on the half-life of a radioactive material. So the half-life of a radioactive material is the amount of time it takes for half of the substance to change from its original radioactive state to a non-radioactive state by emitting energy in the form of radiation. So in other words, half-life is just the amount of time it takes for radioactive material to decay by half, right? This is given through this exponential function. A of t equals P times 1/2 to the T over H. Same P, same A, same T. Only difference is the exponent is T over H. So T is the time, and H is the half-life of that material. So before we calculate this, we have to figure out what T divided by H is, right? Whatever that is. Also, I mean, clearly you can see that the base is always going to be 1/2. So this is always an exponential decay function. Okay. So let's say a radioactive material has a half-life of 2 years. okay? And let's say that you start out with 800 grams. So let me ask the question, how long would it take, or not how long would it take, how much of that radioactive material would be left after, let's say, 10 years? Well, let's find out. So A of 10, that's my P, which is 800, times 1/2 to the 10 divided by 2, which is 5. So that's 800, and I'm going to use a decimal here. You can use a decimal if you want to, times 0.5 to the 5th power. So let's figure out how much is left after 10 years. 800 times 0.5 to the 5th power. 25 grams left. Yes. Multiple applications of exponential functions, but all of which can be and are used pretty much every day.